Object-oriented programming, often shortened to OOP, might sound like a complicated term, but the basic idea behind it is quite natural. Think about the world around you. It's full of objects. Your cat, your computer, your favorite coffee mug. Each of these objects has certain characteristics, like the cat's color or the mug's capacity, and things it can do, like the cat can purr or the computer can run programs. OOP is a way of writing computer programs that mirrors this real-world organization. It helps us structure our code by thinking about these objects and how they interact with each other, making our programs easier to design, understand, and manage, especially when they start to get big and complex. In OOP, we first design a blueprint for an object. This blueprint is called a class. For example, you could have a class. This class would define what all cars have in common, like having wheels, an engine, and a color. It would also define what cars can do, like starting, stopping, and accelerating. Once you have this blueprint, the class, you can then create actual individual cars from it. Each individual car you create, like a red Ferrari or a blue Honda, is called an object or an instance of the class. Each object will have its own specific details, like its particular color or current speed, but they all follow the rules set by the class. Using OOP allows programmers to build software in a more modular way. Instead of writing one massive block of code that does everything, you can break down the problem into smaller, manageable pieces, these objects. Each object is responsible for its own data and its own behaviors. This makes it easier to test parts of your program independently and also makes your code more reusable. If you've designed a good class for one program, you might be able to use it in another program that also needs to simulate cars, saving you a lot of time and effort. It's like having a set of well-designed Lego bricks you can use to build many different things. So, the core idea of OOP is to think about your program in terms of these self-contained objects. These objects hold their own information, which we call attributes or properties, and can perform actions, which we call methods. When you want something to happen in your program, you typically tell an object to perform one of its actions. This approach helps keep everything organized, makes code easier to update without breaking other parts, and generally leads to more robust and flexible software. Understanding this basic concept of objects and classes is the first step to understanding cool Python features like constructors and destructors, which we'll dive into next. They are all about managing the lifecycle of these objects. Now that we have a basic idea about objects and classes, let's talk about how an object gets born and set up in Python. When you create a new object from a class, Python automatically calls a special method to get that object ready. This special method is called a constructor. In Python, the constructor method is always named. Those double underscores at the beginning and end are a convention in Python to indicate that this is a special method with a specific purpose, and you shouldn't just name your regular methods this way. Think of the method as the official welcoming committee for your new object, responsible for getting it all set up. The primary job of the constructor, this method, is to initialize the newly created object's attributes. When an object is first created, it's like a blank slate. The constructor's role is to give it its initial state, its starting values. For example, if you're creating an object, the constructor might set its initial and. Without a constructor to set these initial values, your new object might not be in a usable state, or it might not have the specific characteristics you want it to have right from the start. It's the part of the process that says, okay, new object, here's your name, here's your age, welcome to the program. You don't usually call the method directly by its name, instead, Python calls it for you automatically whenever you create a new instance of a class. For example, if you have a class named and you write, Python first creates a new, empty object, and then immediately calls the class's method on that new object to set it up. This automatic nature makes constructors very convenient because you don't have to remember an extra step to initialize your objects. It's built into the creation process itself, ensuring every object starts off on the right foot. So in simple terms, the constructor is a special function inside a class that gets your object ready for action. It's where you put the code that needs to run every single time a new object of that class is made. This ensures that all your objects begin their existence with all the necessary information and are in a consistent, predictable state. This setup process is fundamental to making OOP work smoothly because it guarantees that objects are properly configured before you start using them in your program, preventing a lot of potential headaches down the line by making sure they are ready to go. Creating a constructor in Python is actually quite straightforward once you know the magic name. Inside your class definition, you define a method named. The very first parameter of this method, and indeed any method inside a class, must be. This parameter is a reference to the instance of the object that is being created. Python automatically passes this reference to the method, so you don't have to worry about providing it when you call the class to make an object. Think of as a way for the object to refer to itself, allowing it to store and retrieve its own data. After, you can add any other parameters that you want your constructor to accept. These parameters are used to pass in initial values for the object's attributes. For example, if you're creating a class, you might want to pass in the and when you create a new book object. So your method might look something like. Inside this method, you would then use to assign these passed-in values to the object's attributes like and. This way, each object can have its own unique title and author right from its creation. Let's look at the syntax more closely. You start with, just like any other Python function. Then comes the special name. The parentheses follow, containing as the first argument, and then any other arguments you need, separated by commas. Inside the method, lines like are very common. Here, creates or updates an attribute on the object itself, and is the data you're storing in it. This process of assigning values to is what truly initializes the object, giving it its specific characteristics from the moment it comes into existence. It's important to remember that the method doesn't return a value in the way most functions do, or rather it implicitly returns, and you shouldn't try to make it return anything else. Its main job isn't to give back a result, but to modify the newly created object referenced by setting up its internal state. When you write, Python does the work of creating the raw object, then calls behind the scenes. The variable then holds the fully initialized object, ready for you to use in your program. Constructors, the methods in Python, play an absolutely vital role in object-oriented programming. Their primary importance lies in ensuring that every object, when created, starts its life in a well-defined, consistent, and usable state. Imagine trying to drive a car that hasn't had its engine installed or its wheels bolted on properly. It wouldn't work very well, or at all. Similarly, an object in a program needs its essential attributes to be set up correctly from the very beginning. Constructors are the mechanism that guarantees this initial setup, preventing objects from being in some weird, incomplete, or unpredictable state when you first try to use them. This initialization process is crucial for the reliability of your code. If objects are not properly initialized, they might lack necessary data, leading to errors later on when you try to access attributes that don't exist or call methods that rely on that missing data. For instance, if an object requires A to function, the constructor can ensure that A is provided and stored every time A is created. This makes the rest of the code that interacts with objects simpler and safer, as it can assume that a will always be present. It takes the guesswork out of an object's initial condition. Furthermore, constructors allow you to create objects that are customized right from the moment of their creation. By passing arguments to the constructor like a name and age for an object, or a URL for an object, you can create many different instances of the same class, each with its own unique starting characteristics. This flexibility is a cornerstone of OOP. Instead of creating a generic object and then having to call multiple other methods to set it up, the constructor handles this in one clean atomic step. This makes your code more readable and easier to understand because the creation and initial configuration of an object happen in a single, clear statement. Ultimately, constructors enforce a contract for object creation. The class designer, by defining the method and its parameters, specifies what information is mandatory to create a valid object of that class. This helps prevent errors and makes the class easier to use correctly. If you try to create an object without providing the required arguments for its constructor, Python will raise an error, immediately telling you that something is wrong with how you're trying to make the object. This immediate feedback is much better than having an improperly configured object silently causing problems later in your program's execution, making debugging a much more difficult task. Section 5. Constructors in Action. A simple hello world for objects. Let's see constructors in action with a simple example. Imagine we want to create a program that deals with different types of pets. We can start by defining a class. Every pet will have a name and a species. We can use the constructor to set these attributes when a new object is created. So, inside our class we'll define our method. This method will take as its first argument, followed by and as additional arguments. These will be the pieces of information we need to provide every time we make a new pet in our program. Here's how the class with its constructor might look in Python code. Python class pet def, self-name species, print fey new pet is being welcomed. Self.name =name self.species =species print. This pet's name is self.name and it is a self.species I. Now let's create a couple of pet objects. Python pet1 pet whiskers cat, pet2 pet buddy dog. In this code, when we write, Python first creates an empty object, then it automatically calls the method. The parameter inside refers to this newly created object. The string is passed as the argument and is passed as the argument to the method. Inside the method, the line takes the passed-in, whiskers, and stores it as an attribute called on the object itself. Similarly, stores cat as the attribute on. The statements are just there to show us when the constructor is being called and what values are being set. The same process happens for, but this time with buddy and dog. Now, and our distinct objects, each with its own, and all thanks to the constructor setting them up correctly at the moment of creation. After these objects are created, you can access their attributes. For example, you could write and it would output whiskers, and it would output dog. This demonstrates how the constructor successfully initialized each object with its specific data. Without the method doing this setup work, and would just be empty shells, and trying to access would likely cause an error because the attribute wouldn't exist yet. This simple example clearly shows the power and necessity of constructors for creating fully formed and usable objects. Section 6. The other side of the coin. Understanding destructors. Just as constructors are special methods called when an object is created, Python also has a concept for a special method that is called when an object is about to be destroyed or cleaned up. This method is often referred to as a destructor. In Python, the destructor method is named. Similar to the double underscores indicate that is a special method with a particular meaning to the Python interpreter. Its primary purpose is to perform any necessary cleanup tasks before the object is removed from memory. Think of it as the object's farewell routine, tidying up any messes it might have made during its lifetime. It's important to understand that in Python, memory management is largely automatic thanks to a process called garbage collection. The garbage collector keeps track of objects and automatically reclaims the memory occupied by objects that are no longer being used or referenced by any part of your program. Because of this, you don't usually need to write methods just to free up memory. Python handles that for you. This is quite different from some other programming languages like C++, where destructors are critically important for manual memory management. In Python, the role of is more specialized, so if Python's garbage collector handles memory, when would you actually use? Destructors in Python are typically used for releasing external resources that the object might be holding onto. These could be things like open files, network connections, database connections, or locks on certain resources. If your object opened a file, its method could be a place to ensure that file is properly closed before the object disappears. This helps prevent resource leaks, where your program holds onto resources longer than necessary, potentially causing problems for itself or other programs running on the system. However, there's a significant caveat with methods in Python. Their execution is not absolutely guaranteed and the timing can be unpredictable. The method is called when the garbage collector decides to reclaim the object. This might happen immediately when the last reference to the object is gone, or it might happen later, or in some rare cases, like when an object is part of a reference cycle and the cycle collector can't break it, or during Python interpreter shutdown, it might not be called at all. Because of this unpredictability, relying solely on for critical cleanup tasks is often discouraged. Instead, using explicit methods or context managers, the statement, is generally preferred for managing resources reliably. Section 7. Crafting a destructor, the basic blueprint. Just like the constructor, the destructor is a special method that you define within your class. The syntax for defining a destructor is very similar to that of any other method in a Python class. You use the keyword, followed by the special name, and then parentheses containing the parameter. The parameter, as always, refers to the instance of the object that is about to be destroyed. This allows the method to access the object's attributes or call its other methods if needed during the cleanup process. Though this should be done with caution, as the object's state might be partially dismantled. A typical method usually doesn't take any arguments other than its job is to perform cleanup related to that specific object instance. For example, if an object represents a temporary file created on disk, its method might contain code to delete that file. The operations within should ideally be self-contained and not rely heavily on other objects or global state if possible, because the state of the rest of the program during garbage collection can be uncertain. It's best to keep destructor logic relatively simple and robust. Here's what a very basic method might look like inside a class Python class: myResourceHandler, def, self_resource_name, self.resource_name, =resource_name print, freesource self.resource_name, acquired. In this conceptual example, when an object of is no longer referenced and the garbage collector decides to reclaim it, the method would be invoked. The statements inside would then execute, indicating that the cleanup process for that specific resource is underway. It's crucial to reiterate that you should not call directly like. Doing so doesn't actually destroy the object, it just runs the code inside your method. The actual destruction and memory deallocation are handled by Python's garbage collector. The method is simply a hook that Python calls if it can just before the object is truly gone. Therefore, its primary use is for releasing external resources or performing final logging, rather than for managing the object's memory itself, which Python does a good job of on its own. Section 8. When do you need a destructor? Practical use cases. While Python's automatic garbage collection handles most memory cleanup, there are specific scenarios where defining a method, the destructor, can be quite useful. The most common use case is for managing external resources that are not automatically handled by Python's memory manager. These are things like file handles, network sockets, database connections, or hardware device interfaces. If your object opens a file when it's created or establishes a network connection, you need a way to ensure that file is closed or that connection is terminated when the object is no longer needed to free up those system resources. For instance, imagine you have an object that locks a file to prevent other processes from modifying it while your object is working with it. The method could be a place to ensure this lock is released. If the lock isn't released, the file might remain inaccessible even after your program, or that part of your program, is done with it. Similarly, if an object maintains an active connection to a remote server, the destructor could attempt to send a disconnect message or properly close the socket. This helps maintain system stability and prevents resource exhaustion, which can occur if too many files are left open or too many connections remain active. Another potential use for destructors is logging or performing some final action when an object's life ends. You might want to log a message indicating that a particular object, perhaps one managing a critical task, has finished its work and is being cleaned up. This can be helpful for debugging or auditing purposes, giving you a trace of the object's life cycle. For example, an object representing a long-running background task might use its destructor to log its completion status or total runtime before it disappears, providing valuable insight into the application's behavior over time. However, it's essential to be aware of the limitations and potential pitfalls of. As mentioned earlier, their execution is not strictly guaranteed, and they can make objects harder for the garbage collector to reclaim if they create reference cycles or if errors occur within the method itself. Exceptions raised in are ignored and printed to. For critical resource management, Python offers more robust and predictable mechanisms, such as the statement or context managers, using the statement. These tools provide explicit control over when resources are released, making them generally preferred for tasks like closing files or releasing locks, as they offer stronger guarantees than a method alone. Section 9. Destructors at work. A farewell example and final thoughts. Let's put together a small example to see a destructor method in a conceptual way. We'll create a simple class called that pretends to open a file in its constructor and then closes it in its destructor. We'll include print statements to observe when these methods are called. Remember, in a real-world scenario for file handling, using a statement is usually the better approach for reliability, but this example will illustrate the destructor's behavior. Here's the code for our class Python class file handler, def self_filename, self.filename =, filename self.file_ is _, open =, true hash. Simulate opening the file print, file handler created for self.filename. File is now open. Def, self. If self.file called for self.filename, print f closing file, self.filename. Self.file underscore is underscore open equal sign. False hash simulate closing the file, else print f called for self.filename, but file was already closed. Python print creating file handler object, fh equal sign file handler, my document.xt print file handler object f exists. Print, deleting reference to fh, del f hash. This removes the reference, might be called soon after. Print, reference to fh deleted, program continuing for a bit. Time.sleep, 1 print, program finished. When you run this code, you'll first see the message from as is created. Then, when is executed, the reference to the object is removed. If this is the last reference, the Python garbage collector may soon decide to reclaim the object, which would then trigger the method. The statements inside will then show that it's attempting to close the file. The exact timing can vary, which is why the is added, to give the garbage collector a chance to run before the program fully exits. In summary, constructors and destructors are special bookend methods in Python's object-oriented programming model that manage the lifecycle of objects. The constructor is your object's welcoming committee, called automatically when an object is created. Its crucial role is to initialize the object, setting up its attributes and ensuring it starts in a valid and usable state. This setup is fundamental for creating customized and reliable objects right from their birth, making your code more robust by ensuring every object is properly configured before use. Destructors, on the other hand, are like the farewell party, called, if at all and at an unpredictable time, when an object is about to be destroyed by the garbage collector. While not typically used for memory management in Python, as that's handled automatically, they can be useful for releasing external resources like open files or network connections, or for final logging tasks. However, due to their less predictable nature, more explicit resource management techniques like statements are often preferred for critical cleanup. Understanding both constructors and destructors gives you a fuller picture of how Python objects live and die, allowing you to write more effective and well-structured object-oriented code.